Good afternoon, class. Today is our final Science 10 lesson. And today, what we're going to talk about is phases. What I mean by phases is the solid, liquids, and gases, and how objects can change from a solid to a liquid, and then a solid or a liquid to a gas. Now, every time you have a phase change, you either have an absorption or a release of energy. If you think about ice creating liquid, you need to heat that ice up. So what happens is those bonds are being broken by that energy, and then you have a phase change, and then your temperature rises. Now, going from that solid to a liquid state is called heat of fusion. So heat of fusion is the amount of energy, which again we're going to use that symbol of Q, needed to change 1 mole. Aha! Chemistry. 1 mole of a substance from a solid phase to a liquid phase. Remember that a mole is just a chemistry way of saying how much of something you have. It's a really big number. Regardless, I'm going to keep it really simple for this year because of everything going on. We're just going to use moles. So the amount of energy needed to change 1 mole of a substance from solid to liquid. That's heat of fusion. Then, if you look at the other way, the amount of energy that's released during liquid to solid is called the heat of solidification. So when you solidify something. One thing that's really important to know, while something is changing phase, there is no change in temperature. So let's take a look at ice. If we have a block of ice, you're going to heat it up to create water. Now, there's a point where all of that heat is being used to break bonds, and it's not being used to actually create kinetic energy in the particles. That means there's no increase of temperature even though there's heat being absorbed. So there's no change in temperature during a phase change. We're going to look at the phase change graph a little bit later, and I'll reiterate that. Also notice that we have two different verbiage here. Heat of fusion is the amount of energy needed, so that would mean absorbed, to change from solid to liquid. So that would be the amount of energy needed to melt ice and then to create water from that ice. Whereas if you go the other way, from a liquid to a solid, so when you freeze ice, that ice actually gives off energy. So it releases energy, which is another thing that's not really common sense. Now let's look at the other way, from a liquid to a gas or from a gas to a liquid. Liquid to a gas is called heat of vaporization. It's the amount of energy, again, needed to change 1 mole of a substance from liquid to vapor. So again, energy is absorbed. Just like before, there is no change in temperature while an object is undergoing a phase change. There is still energy added, but not a change in temperature. And then to go the other way, from a gas to a liquid, is called heat of condensation. So it is released. When you have condensation, you're releasing energy. Let's take a look at that graphically. So this is called a heating curve, and it shows the phase changes of any object. I just used water because we all know what those numbers are for water to change phase. But what's really interesting is that as it goes up, it's kind of linear. That's fine. But this is going to be considered ice. But at number 2 here, see how it plateaus? This part here, that's where it's undergoing a phase change. We know what happens around that 0 mark. That's where water freezes. And the phase change, in this case, this is our H fuse. We use a little subscript for FUS for our heat of fusion. This area here is where that phase change occurs. But what I want you really to notice is that the temperature here and the temperature here are the same. We haven't increased our temperature. Even though you're going from ice to liquid, there's no increase in temperature while it's undergoing a phase change. But what is happening is that more energy is being absorbed. So all that energy there doesn't increase the temperature, it just changes phase. Then you go on for a while in this area, and you have water. I might move that over here. We have water in phase 3, or in section 3 here. That water is just normal water. Between 0 and 100 degrees Celsius, you have water. But then when you get to 100 degrees Celsius, the same thing happens, where it's changing phase. This is going to be H vaporization. It's another phase change. That's going from a liquid to a gas. This is liquid, this is gas. This is solid, this is liquid. Alright, so that's kind of the heating curve, and then here we have gas, obviously. If we were to go in this direction, it would be solid to liquid, and then liquid to gas. If you go in this direction, you have gas to liquid, and then liquid to solid. Another thing you have is a difference in energy. When you go from solid to a liquid, energy is being absorbed. Same with when you go from a liquid to a solid. Again, you're taking that energy and you're breaking up the bonds. When you go from gas to a liquid, you're recreating those bonds and energy is released. Which is super strange, because you think like going from liquid to a solid, that's freezing, but it's actually giving off heat. So that's one thing that students really get hung up on. And it's super important for you to know. To calculate these heat of fusion and heat of vaporizations, a lot of the times this heat of fusion is going to be given to you, but sometimes we want to find out our experimental values. And it's really a super simple formula. Heat of fusion is Q over N, and then heat of vaporization is the same, Q over N. Now that's just really important that you know which step along the process we are at. So if we're at 2 or if we're at 4, you will need to know which one to use and which constant to use. So let's try one example. I just have one and that's it. We're going to calculate the amount of energy that's absorbed or released when 18 moles of water, which has a heat of fusion of 6.01 kilojoules per mole. I didn't talk about that, but this is in kilojoules, this is in moles. So our HFuse and HVAP are measured in kilojoules per mole. So when 6.01 kilojoules per mole for HFuse, and our HVAP is 40.65 kilojoules per mole. When they transition from gas to a liquid. Okay, so let's look up here. I might just get rid of all my stuff. Gas to a liquid, which would mean from 5 to 3, this direction. Now, is that HVAP or HFuse? Well, it is HVAP. And is energy being released or absorbed? It's going this direction, so energy is released. Let's do the math then. Gas to a liquid, we're going to use HVAP, and HVAP is equal to Q over N. We have HVAP, we have N, we just need to find Q. Remember, we're trying to calculate the amount of energy, which is our Q value. We want that in joules or kilojoules. So let's rearrange the formula. We're going to multiply both sides by N, and you get N times HVAP is equal to Q, which in our case is 18 moles times 40.65 kilojoules per mole. Our units will cancel, which is great. That's how you can always tell if you're right. And we get 731.7 kilojoules. Alright, now let's look from solid to liquid. So solid is down here and liquid's up here. We're going this direction. So energy must be absorbed. It's endothermic. So if energy is absorbed and it's going from solid to a liquid, that's going to be our H fuse. And that's equal to Q over N. Again, we want to isolate for Q. We're going to get that same formula of N times H. This time it's H fuse is equal to Q. 18 moles times, this time we have to use the H fuse number of 6.01 kilojoules per mole. And we end up with 108.18 kilojoules. And that's it. That is as difficult as we're going to make it in Science 10 for the 2020 school year, or at least first semester. If you guys have any questions about anything, please feel free to reach out. I am always available. Just send me an email or message me on Discord. It has been a pleasure teaching you this year, and best of luck in grade 11. Take care.